Okay, in 11.8 يا شباب, we said that we have here what is called power series. Okay, when A is 0, we have it in this form. This is of course a power series centered at A or about A or at A, and this is at 0. Okay, this is what we have done in 11.8, and you know how to find the interval of convergence, the power of the radius of convergence, and so on. So what we have done in 11.8 and 11.9, mainly, I'm talking about mainly, not everything. In 11.9, we have found that this is specific when Cn is 1 and A is 0, this case. When we have x to the power n, when n starts from 0 again to infinity, we have found that this equals to what, ya shabab? This is a convergent geometric series. It is a convergent geometric series equals to what?
1 over 1 minus x.
Provided that it is not for any x, طبعا. This is only for what?
X less than 1.
For x between -1 and 1. Yes. So this is 11.9. We call this series representation for functions, or how to represent a series as a function as a series. What we will do today in 11.10. In 11.10, we will try, طبعا here يا شباب, as I said يا شباب, here Cn is 1. The coefficient that we have here, it is 1. So when it is 1, you have this. So it is, of course, the coefficient. This is called the coefficient. Now today we will try to find if we have a power series, like in general, x minus a all to the power n. If we have a convergent power series within the interval of convergence, we have a sum. The sum will be a function of x, like this. This is a function of x. This is the sum of the power series. So if we have a convergent power series, let's say within the interval of convergence, where x minus a is less than r is the radius of convergence. If we have it as a convergent power series and it converges to f of x, the question is there a relationship between the coefficients here and the function here? How to find this relationship and how to determine these coefficients in terms of the function. By the way, here this coefficient here is 1, so it wasn't clear for us what happens here. It is the first term طبعا, but for the others this is a geometric series. It is something else. But how to do that in general for any power series, for any power series within its interval of convergence? In fact, Taylor, he has a brilliant idea, and it was in fact a big discovery in mathematics, that he can do that. He can expand, of course, any power series. If you have the function, you can find its. So what we have a function, and we want to write it as a power series. This is the question. So how to do that? If the function is like 1 over 1 minus x, or its derivative or its integral, it is easy. This is of course 11.9. We have done that. Today also this will be included here if you want. So this will be just a special case from what we have today. So in general, if you have a function and you want to represent this function as a power series, how to do that? Okay, we will follow the Taylor theorem, and I will show it in the next slide. Let's see what has been done by Taylor, what he did in his theorem. He said, I have a power series that is convergent over this interval. If it is convergent, of course, it has a sum, so its sum is a function. You can expand, by the way. It will be better to expand the summation here to make it more clear for you. Now look what will happen. What is the value of the function at a? If you evaluate the function at A, what will happen? This will be 0, 0, 0, 0. We have what? C at 0. Is that clear? Then let's now start differentiating. Let's take the first derivative for this. For this one, take the first derivative. What will be the first derivative? And you can differentiate this, as you know, as we did before. So when you differentiate the constant, it will be 0 plus the derivative of x is 1, so it will be c1. The derivative of a, of course, is 0. It is a constant. We are differentiating with respect to x. Now this will be c1, c2, 2c2, 3c3 squared, 4c4 to the power 3, and so on. But you know that the derivative will still have, of course, here the same radius of convergence. Now this, if you substitute now, ya shabab, if you put x equals to a, if you evaluate the function at a, this will be 0, 0, 0. What we have? C1. So the first, the value, طبعا يا شباب, you know that the value of the function at a, now it is C1. So I think also you have seen this before, that we said that the zero derivative of a, it is here C0. Here the first derivative is C1. If you continue, Shabab, differentiating, so if you differentiate again, find the second derivative, the derivative of this constant will be 0, the derivative of this will be 2c2, and then this will be 3, 2 times 3, c3, x minus a, then 3 times 4, c4, and so on. If you evaluate this at a, again, this will be 0, 0, and you will have 2c2. So we have now the second derivative of at a equals to 2c2. Differentiate for the third time, this will be 0, the derivative of this will be 0, the derivative here will be what? 2 times 3 times c3 times x, the derivative of x is 1. Then here you will have 2 times 3 times 4, c4, x minus a. Then 3, 4, 5, c5 to the power 2, and so on. If you evaluate at 3, what you will have? At a, if you evaluate the third derivative at a, this will be 0, 0, you will left up with this. 2 times 3 times 3. 2 times 3, C3, it is in fact 2 times 3 is 3 factorial. So what we have here, we have the third derivative at a equals to n factorial. Here 3 factorial, not, we will generalize that. So can we say the same here? What is 2 factorial? 2 factorial is 2. So this is also 2 factorial. What is 1 factorial? Also 1 factorial is 1. So what is 0 factorial? Also 0 factorial is 1. So this is equals to C0. So here we have, of course, C0. Here we have C1. Here we have 2C2. Here we have, of course, 6C3, the factorial of 3. So can we generalize this now? We will use this for generalization. So what will be the nth derivative if you continue doing that? It will be n factorial Cn if you evaluate it at a. So now, ya shabab, we have started with f of x equals to Cn x minus a all to the power n start from 0 to infinity. And we have found that the nth derivative at a equals to what? N factorial Cn. So what is Cn? What is the coefficients here? They are just the nth derivative evaluated at a divided by n factorial. So we can say that f of x equals to, this is easy, x minus a to the power n, this is the power series. Now here we will write what? The nth derivative at a over n factorial. So this is, of course, the coefficient Cn can be found in terms of f and its derivatives evaluated at the center of the power series. I have said that before, so let's now read together the Taylor theorem. This is called Taylor theorem. Taylor theorem says, if f has a power series representation or expansion, If f has a power series representation at A, what does that mean mathematically? Mathematically, we have this within this interval. Then what? Then the coefficients, they are also called Taylor coefficients. Then the coefficients are given by this formula, the nth derivative at A over n factorial. This is Taylor. This is called Taylor series of the function f at A, or at about A, or centered at A. There is a special case and a special interesting case when A is 0. When A is 0, they give it also a name. They call it Maclaurin series, of course, to honor the mathematician Maclaurin. They just, when you replace A here by 0, just it will be, this will be 0, this will be 0, so it will be like that. F of x will be the nth derivative at 0 over n factorial x to the power n. If you expand it, it looks like this. F at 0 plus f derivative at 0 x, f derivative of plus, and so on. See, it is easy to be memorized. Why? When you have x squared here, you have 2 factorial. So it is 2 factorial power 2 second, 2 derivative, the second derivative. First derivative, first factorial, first power. Here, of course, here you have, of course, here the derivative of 0 over 0 factorial, x to the power 0. So it is the same. So this is, of course, much easier to be memorized like this. Are you ready now to start to set up some examples about this? Let's take, for example, the easier one, e to the power x. Find the Maclaurin series. So which one of them is Maclaurin? The last one, when a is 0. So here a is 0, so we will expand it. The Maclaurin series is what, Shabab? It is this one. The nth derivative at 0 over n factorial x to the power n. This is Maclaurin series. Okay? So what we want to find, Shabab, just we want to find the nth derivative. The nth derivative at 0. Who can tell me what is f of x? F of x, it is e to the power x. What is the first derivative? Itself. The second derivative, the third, the fourth. So what is the nth derivative?
Itself.
Itself. So what will be the value of the function at 0? At the value of the nth derivative at 0. It will be e to the power 0, which is what? 1. So this will be what? 1. So easy. Here we are. So what we can say? We can say that e to the power x equals to this. Just we need to make sure where. Is it for all x or not for all x? So let's come to the details. That was the summary. Let's come to the details. As I said, Shabab, the nth derivative is itself. So the value of the nth derivative for any derivative, it is 1. Now, according to the Taylor series at 0, what is Taylor series at 0? It is the Maclaurin series. So you can have, if they said this or this, they are equivalent. Now it will be like this. I said this is 1, ya Shabab. So it will be x to the power n over n factorial. What is it? 1 plus x over 1 factorial plus x to the power 2. This one, indeed, it is x to the power 0 over 0 factorial. 0 factorial is 1. And so on. Now, where it is valid, we need to find the radius of convergence. I think he asked about it. What is the radius of convergence? To find the radius of convergence, what you need to do, you need to find or to use the ratio test. If you remember, this is 11.8. Just divide an plus 1 by an, so multiply with the reciprocal. Now this will be cancelled, and with this, and you'll have here x. This is n factorial will be cancelled with this, and you will have n plus 1. So now what we end up with is the absolute value of x over the absolute value of n plus 1. But n plus 1 is positive, so without absolute value. Now when n goes to infinity, absolute value of x over n plus 1 will goes to 0. Regardless what is x, because x, it is not n, it is not going to be infinity. Of course, here we have 0. The limit will be a fixed number over infinity, so it is 0. and this 0 is less than 1. So by the ratio test, this series is convergent for what? For any x. It doesn't depend on x, yes, shabab. So this is equals to 0 for any x. It is less than 1 for any x. So this means that this series converges for all x. And the radius of convergence is infinity. Also, the interval of convergence is from negative infinity to infinity. So it is amazing, ya shabab. We have this formula valid for all the values of x. We will write it here as a theorem. E to the power x equals to this power series n start from 0 to infinity for x to the power n over n factorial for all x, for any x. This is amazing, ya shabab. You know how to convince someone that say for you that e to the power x. What is e to the power x? I don't feel it. I need more explanation about it. What is it indeed? In terms of something that I know, ya shabab, this is, of course, you know that the exponential function, the logarithmic function, the trigonometric function, the hyperbolic function, they are not algebraic, by the way, in the same sense. They called these, I think, transcendental functions. They are higher level functions. So now, in fact, if you look at this, it is just simply 1 plus x squared over 2 plus x to the power 3 over 6 plus x to the power, and this 6 is 3 factorial, plus this is 4 factorial. So it is the sum of these power functions, these functions that they are power functions, you know. So this is the expansion or the expanding of e to the power x. احنا الحين we expanded, يعني احنا فككناها، يعني حللناها جبريا هذه هي. And this also will give us another representation for the magic number e. You know, Shabab, this Euler number, this irrational number, we have represented in several ways. You remember that we said that e to the power x, it is the limit when n goes to infinity for 1 plus x to the power n all to the power n. When x is 1, you have here 1. And this is in Math 101, we represented the number e as a limit. In Math 102, look what we have. We have it as a power series, infinite power series. In fact, e, it is 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 over 120 and so on. So this is what we usually do. We represent something new in terms of something old that we have an idea about. We know the power functions and we can use them. طبعا this is يا شباب Maclaurin series. Maclaurin series for e to the power x. And what is good about it, as I said, it is for all x. Find the Taylor series of the same exponential function, but this time at a equals 2. What is that? This is sigma if the nth derivative at a. What is a in our case? 2 over n factorial x minus 2 all to the power n. This is the power series, the Taylor series of this function. And of course, we will see if it is valid always for any x or not. But it will be, of course, by the ratio test. Now the question is, what is this, Shabab? What we need to find is this one. So who can tell me what is this? F of x, it is e to the power x. What is the nth derivative? Itself. So what is the nth derivative at 2? E to the power 2. So this is just e to the power 2. And we are done. This is the Taylor series. If you apply the ratio test for this one to find the radius of convergence, you will find that it is the same. I think I mentioned this here for you. Yes. As an example 1, the radius of convergence is still, of course, infinity. So we can say, Shabab, also that e to the power x equals to this, if you want to have it in terms of x minus 2. So it is just like a kind of shifting. But of course, when you're shifting here, you have the new coefficient, not the same one. This one, in our case, in the previous case, it was 1. Find the Maclaurin series for sine x. The Maclaurin series is the Taylor series at 0, so at a equals 0. So how to find that, ya shabab? What is the Maclaurin series? The Maclaurin series is the nth derivative at 0. This is our f of x. F of x now, it is sine x. So it will be just like that, x to the power n starts from 0 to infinity. The question is, what is the nth derivative at 0 of this? Who can tell me? What is the nth derivative of sine at 0? This is what you need to find. To do that, we will do it step by step like this. What is f of x? It is sine x. What is the derivative of f? What is the derivative of sine? Cosine. Evaluate the derivative, the first derivative at 0. What we will have? 1. Cosine 0 is 1. Now the third derivative, the second. Let's start with the second. The second derivative of cosine is negative sine. Evaluate at 0. What you will have? Negative sine 0. Sine 0 is 0. The third derivative, negative cosine x, will be negative 1. The fourth, is it clear? Can you stop, or you need to do more derivatives? The fourth derivative, sine x, and at 0 it will be 0. So this is what we want to focus on. So can you tell me now what is the nth derivative?
Alternative.
Unfortunately, it is of course 0 or 1, 0, negative 1, 0. So what is that? So when n, notice that when n is even, it is what? It is 0. If n is odd, it is what? 1, positive 1, negative 1, positive. It is alternating. It starts with positive 1. So with negative 1, you can write it n minus 1 or n plus 1. So to combine these together, ya shabab, what we can do, we can expand it. Let's write the expansion and then we will decide about the final form. So we will do what? The Maclaurin series, as I told you, shabab, I have written this for you here. F n at 0 over n factorial x to the power n. N start from 0 to infinity. Now, when n is 0, we have this. The 0 derivative at 0 over 0 factorial, it is f at 0. Okay? The first derivative at 0 over 1 factorial x. When n is 2, we have this. When n is 3, we have this. Now let's substitute, ya shabab. What is f at 0? F at 0, it is 0, so this will be gone. It will be 0. F prime, it is 1, so we will have 1x. Plus, the second derivative, it is 0, so this is gone. This term will be 0. Plus, the third derivative is negative 1, so we will have negative 1 over 3x to the power 3. What do you expect? The fourth derivative, so if we continue, the fourth derivative will be 0. Minus the plus, it will be plus 1 over 5x to the power 5. Minus or plus 0, minus, this will be minus this time, and so on. You will have it like that. So if you expand it, you will have the following power series. X minus x to the power 3 over 3 factorial plus x to the power 5 factorial negative x to the power 7 over 7 factorial. How to represent this as a power series? Of course, you can write it as sigma. Notice that it is alternating positive, negative, positive, negative. So you will start with from 0. So you will start with n. When n is 0, it is positive, correct. Now what you notice here, shabab, you have 3 factorial, 5 factorial, 7 factorial. Here, by the way, you have 1 factorial. So what is that? They are odd numbers. So you can represent the odd numbers by 2n plus 1 factorial. Also the powers, it is to the power 1, 3, 5, 7. All the even powers has been cancelled because they are equal to 0. So this is 2n plus 1. So now we can, you can use the ratio test also to find out that this is convergent for all x. So we have now a representation for sine x as a power series for all x. So just I want you to remember that this is sine x equals to this. And how to remember it easily يا شباب. ببساطة you remember that sine is odd. Do you remember that it is odd function or not? This is not difficult to be memorized. Now look at the powers here. 1, 3, 5, 7, odd also. And this is also something beautiful about mathematics. It is consistent. You cannot find a contradiction. If there is a contradiction, this is not true at all. This is false. And you know that here we have also odd function, odd power. Good. Let's do the same for cosine. طبعا. If you want to find the Maclaurin series for cosine, again, you need to find, of course, the function, then the second derivative, then the third derivative, and so on, until the nth derivative, if you can, of course. Then evaluate them at 0, because we want to find Maclaurin series. So this is easy. You can do it as we did for sine, you can do it for cosine. But there is a short way that we can do. Of course, as before, because now we have sine, we can, of course, make it short when we evaluate cosine. What we can do, ya shabab? Ya Ziad, what do you think? What we can do to find cosine in a short way? Instead of this, instead of doing this, we can do something, ya Ziad. What is it? Ziad? Are you here, Ziad? Is Ziad here, ya shabab, or not? Hamad al-Dail. Hamad, are you here, Hamad? Yes, Hamad, what do you think? What can we do instead of finding all what we did in the previous example? الحين احنا نعرف what is sin x is. نبغى نعرف الكوساين كمان، كيف راح نسوي؟ منير، we know that منير عزب. ايش رايك يا منير؟ Is Munir here? Munir is not here. عبد الرزاق العنزي. عبد الرزاق are you here يا عبد الرزاق؟ عبد الرزاق العنزي. Okay. So what we can do يا شباب easily is what? محمد الرميح, can you tell me what we can do?
Yes, you said that we can that sine is odd, and but cosine is even. We can say we change the
guarantee. You have to show it. How to show it? Yes, Muhammad رميح. I think يا علي ناس. Do you have an idea? يعني إحنا الحين عندنا ساين يا شباب. إحنا هذه عندنا الساين. كيف نجيب منها الكوساين؟
The derivative.
Maybe the
yes.
Maybe the derivative.
يا شباب that cosine x is the derivative of sine x. Just differentiate this. طبعا أنا قلت يا شباب you can do it as we did before. It is not difficult. Do what we did for sine, do it for cosine. But if you, طبعا this is usually what we are doing in mathematics يا شباب. We use what we have already done, what we know already, and we use it to establish new results. So now we know that sine x, it is x minus x to the power 3 factorial, and so on. So we will just differentiate. We will differentiate this. And you know that we can differentiate the convergent power series term by term. So now the derivative of x is what? 1. The derivative of x to the power 3, it is 3x to the power 2 over 3 factorial. 5x to the power 4 over 5 factorial. 7x to the power 6 over 7 factorial. Now you know that يا شباب 3 factorial, it is 3 times 2 factorial. Well, 5 factorial هو 5 times 4 factorial. Also 7 in general. So what you can do now, you can cancel this 7 with this 7, this 5 with this 5, this 3 with this 3. So you will have what in the denominator here? 2 factorial, 4 factorial, 6 factorial. So you will have in the next step this. And this is now the powers that you talked about, yeah, Munir. I think who mentioned that? Muhammad Rumeh. Yes. Look, it is by default, it will become like that. So in fact, here what we have here, Shabab, what is this one? This one, it is x to the power 0 over 0 factorial. So we have 0, 2, 4, 6, and so on. Also, it is alternating, positive, negative, positive, negative. So how to represent this, of course, as a power series in general? So what we will do, we will write it as what? Positive, negative, positive, negative. It is negative 1 to the power n, start from 0. X to the power 2n. What is 2n? You know, when you have even number, to represent the even numbers, we write it as multiples of 2n. That's it. So now, don't tell me that it is difficult. طبعا يا شباب, you need to remember these formulas for sine and cosine. Also, what is good about them, that they are valid for all x. So now, how to remember them, ya شباب? It is not difficult. Negative 1 to the power n, this is the alternating. Both start from 0, so it is connect them, make a connection between them. You have factorial in the denominator, factorial here. Here it is odd, here it is odd for sine. With sine odd, you know that. With cosine even. It is so easy to be memorized, ya shabab. Okay, find the Maclaurin series, again, when a is 0, the Taylor series at 0, for this function, x cosine x. Of course, you can find the first derivative, the second, the third, until you have the n, and then evaluate at 0, the second at 0. But yeah, Shabab, this is going to be a long process. We can do something easier. What is it?
Put the formula of cosine x.
Use what we have done before. Cosine x, this cosine x is equals to this power series. Just we will multiply it by x, multiply by x each term. It will be just x to the power 2n plus 1. It's done. So instead of doing this from the beginning, you can do it there. It will be a long process, Shabab. If you try to do this one, it is very long, it will be. So this is, use always, this is what I say, Shabab, always to you. Use what you have to find what you want. So we have a formula for cosine. So why I will not use it? Now let's take another example. Find the Taylor series centered at pi over 3. Now this is not Maclaurin series. A here, this is A. A is pi over 3. For this function, sine x, good. So it is going to be the same one before? Of course not. This is another power series over another centered at another point. So how to do that, Shabab? Here, in fact, we cannot use the cosine before because we evaluated at 0. So what we will do, we will use the formal way, the Taylor theorem. We will say that f of x is sine x, evaluated at pi over 3. Sine pi over 3 is square 3 over 2. Find the second derivative, the first derivative of sine x is cosine x, evaluated at pi over 3, which is a half. The second derivative, evaluated at pi over 3. The third derivative, evaluated at pi over 3. If you are sure, you can continue. If you are not sure, of course, you can stop. If you are sure, you can stop. If you don't, continue differentiating. I think, Shabab, we have a pattern now. If you notice, we mainly focus on this. What is our target now, Shabab? What will be this Taylor series that we are looking for? It will be like this. N factorial, x minus pi over 3 all to the power n. Here we have the nth derivative at pi over 3. N start from 0 to infinity. Now we need to find the second, the first, the second, the third, and derivative, and so on. So if you notice, we have square root of 3 over 2, a half, negative square root 3 over 2. And I expect the next one will be what? Negative a half. So it will be like this. It is alternating between square root of 3 and a half and positive and negative. So here we are, Shabab. This is when n is 0, when n is 1, when n is 2, when n is 3. Now evaluate or substitute these derivatives by their values. Now, if we can say that this is x minus pi over 3 all to the power n. This is clear. Here 0, 1, 2, 3. Here we have what? You can say that it is 2 times 2 factorials or n factorial. 0, 1, 2, 3. Yes, it is n factorial. The problem is here. Notice that there is a strange pattern for the sign. It is positive, positive, negative, negative, positive. We cannot represent it negative 1 to the power what? We cannot. We don't have a power here that it will be positive, positive, then negative, negative, then positive. No, we have it like positive, negative, on, off, on, off. Also here, you have square root of 3 over 2. Here you have square root of 3, because this 2 we already considered here. So you have square root of 3, 1, negative square root of 3, negative 1. Again, we have the same. So to avoid this confusion, what we will do, we will write it as a sum of 2 power series. How? We will take the even powers together, and we have a pattern here. So it is 2n even, and here you have square root of 3. This is square root of 3. This is 2 times 2n factorial, the even numbers. And here we have negative 1 to the power n. So it will be now, if n is 0, you will have this. If n is 1, you will have this. Okay, and so on. Now, for the even powers, here 1, here 3. So it is 2n plus 1. Here you have 2 times 2n per 1 and negative 1. So here indeed, this one, this power series for this function can be written in terms of 2 power series if you want to represent it this way. Or you can keep it this way, but it is okay. Writing few terms at the beginning, of course, will give us an idea about how it looks like. Usually, Shabab, they will ask you about few terms at the beginning. If they give you a question like this, they will ask you about a few terms at the beginning. They will not ask for the general form. But even if they did, it is not difficult. I think I wish that the time remaining is enough to solve this example. It is a very important one. Do you remember, Shabab, what we call this? What is this from your previous experience, Shabab? This is binomial when you have 2 terms. There is a formula, Shabab, for this. It is a to the power n, and here you have b to the power n, and here you have it start decreasing and increasing. It will be a to the power n minus 1b, then a to the power n minus 2b squared, and so on. So this is called binomial. Today we will do it with a special case when a is 1 and b is x. You can generalize it, of course, but let's focus on this. If we have this binomial function, 1 plus x all to the power k, how to represent it as, or how to find its Maclaurin series. To do that, we will, of course, do it in the standard form. We will start with what is f of x, then evaluate at 0. When x is 0, you have 1 to the power k. 1 to the power k is 1. Take the derivative. You know how to differentiate this, Shabab. Not difficult. Power. Use the power rule. Then evaluate at 0. When x is 0, this will be 1, and this will be k. You have k. The second derivative, this is the second derivative. Evaluate at 0. It will be k times k minus 1. This will be 1. The third derivative, here it is, k times k minus 1 times k minus 2. Now, you can if you find the nth derivative, it will be like this. Notice, Shabab, here you have k minus 3, k minus 2, so it will be k minus n. Here you have k, you will stop at 2. So also here you will stop at the number before the n. So it will be k minus n plus 1. Here it is. So now when k is 1, when x is 1, when x is 0, you will have this. And this will be times 1. So here we are. Now this is what we are looking for, Shabab. We did find the formula or the nth formula for the derivative. Now what we will do, we will write it as the nth derivative at 0 over n factorial x to the power n. This is Maclaurin series. So here we are, this one, you will replace it here. I think it is there, yes. So this is the Maclaurin series of this function. And of course, you can use the ratio test to see that it is also valid for all x. This is called the Shabab binomial series. And if you, of course, expand it, you will write now, you can say, I think it should be there, yes, you should say that this equals to this power series, but not for all x, for absolute value of x less than 1. So if you use the power series, I think we have done here, if you use the ratio test, you will find that the ratio between this and this, it is what? It is x. To be convergent, this absolute value of x must be less than 1. I think we need to repeat this example again, inshallah, next class. It is, of course, how to represent the binomial, how to find the binomial series. Thank you, Shabab, and see you, inshallah, next Sunday. Have a nice weekend, nice hard working weekend to